Good morning. Okay, so I'm handing out the 248 midterm exam. So the binder should be passing around. Okay, it's in not alphabetic order. It's basically in the last name, first letter, last name, right? Okay, so try not to make a mess of it. Okay. The average midterm is around 67, okay. And it's not bad. And but what's amazing is there are probably around 60 students above 80%. There, a number of them got 100%. Okay, but at the same time, there are also around 60 students below 40%. So this divides here, you know, it's really surprising. So I think we need to bridge the gap right here. Bridging gap does not mean bring down the top portion, right? It's bring up the bottom portion, okay? So I need you to look at the papers. If you notice anything not right, let me know, okay? Make sure you understand the fundamental concept of each one of the questions here. Final exam is not accumulative, but you do need the knowledge of planes, lines. You do need a partial derivative. You do need the concept of line integrals, grading vectors, okay, to carry out the calculations of what we're going to learn, okay? So I'm not going to spend class time to review the midterm anymore. So, but I do need you to go over yourself, okay, and ask yourself if you can redo the question. Any questions? All right. Okay. So let's finish the double integral, and then we're going to get on to a topic called applications of a double integral. In the last lecture, I have one little thing that's not quite finished. I mentioned one property of a double integral. So the property of a double integral, basically, you're integrating, okay, this function f over certain region R. If for certain situation that this region R, okay, can be separated into two regions, okay, then this double integral can be done, okay, by integrating basically over this R1 and R2 separately, okay? Yeah. So chances are you won't be able to integrate this R, the whole thing at the same time, so you're going to have to do it separately. So let's take a look at an example here, okay? Suppose that I have a region R, which is the area bounded by y equal to 2x, y equal to 1/2 x, and x plus y equal to 2. So it's a region bounded by 3 lines. All right. Okay, so first step. Now we're going to integrate, okay, let's say we're going to integrate a certain function, right? So without, let me see, do I give the function here? Maybe we don't need to. Yeah, okay, just in general, okay? So let's say we're integrating certain function f, okay, over this region R. Okay, let's see, in general, how do we carry out this double integral? First step, sketch. So y equal to 2x, slope 2x, y equal to 1/2 x, okay, so that's 1/2 x. Okay, and x plus y equal to 2, that's also straight line. So you can set x over 0, y equal to 2. You can set at y equal to 0, x equal to 2, so that's a straight line somewhere here, right? And so you have a straight lines like this, okay? Yeah. Okay, so here's y equal to 2x, y equal to 1/2 x, x plus y equal to 2. So that's 3 lines. And then the region R right here is this portion. Okay, this portion. So this is a triangle here. It's a triangle. Now, if you're going to carry out this line integral here by using our traditional approach, so if you recall that the second step is to determine the order of the integration, whether you want to do this dy dx or dx dy, right? Yeah. So let's say suppose I wanted to do dy dx like this order here. Okay, so then according to what we learned, so we're going to basically draw what? We're going to draw a vertical line, right? We're going to draw the vertical line and anywhere across this region R. So I'm going to draw it like this. I'm going to draw it here. So draw a vertical line. Okay, so see now the question here is, when I draw my vertical line at here, or when I draw my vertical line over here, right? The purpose of drawing this one here is to find what? It's to find this y mean and y max by looking at the first contact and the second contact points. But because of this special region R here, when I draw the vertical line over here, y mean is here, and y max is here. And when you draw it here, the y mean is here, the y max is here. So it appears like y mean is all the same, right? Yeah, but the y max here and here, they're different. Because the y max over here is represented by what? Y equal to 2x. And the y max over here is represented by y equal to 2 minus x. So they're different. So then basically what it's saying is just drawing one vertical line doesn't cover all the region R, right? It's not a general case study here. Okay? So in this particular case, this is basically, we need to use this knowledge here, this property. Okay? So you separate this integral into two region R's, or even more, just in case. Okay? So how do we separate that? You have to look at this region R here. So in our case, I'm going to basically separate the region R, okay, by drawing a vertical line over here. See, separate this triangle, okay, like this. Okay. So I basically have two regions, okay, on the left and the right side of this vertical line here. Okay. So maybe I'll draw a bigger one in here. Okay, so we're going to separate this whole thing here. Okay, we're going to separate this. And this is going to be R1, this is going to be R2, right? R1, R2, right? Okay, so now I guess once we figure this out, and we're going to be able to carry out this line integral now. Okay, so this original R will equal to R1, okay, plus R2. Okay. So when you write things, I hope you can write everything here. I'm just shortening the writing here, okay? Now, as usual, you draw two vertical lines, okay? One through here, R1, one through this R2, okay? One through R2. Okay. So for the R1, okay, you have basically fx, y, dy, dx. That's the order that we wanted to do. And for R2, same thing. Okay. Yeah. Okay, so first step, find the limits for the y mean for the y variable. For the region R1, the R mean is here. So this is half x, right? This is 2x. So that means for this R1, the mean here is half x. And the max for the R1 is on this line here. So y should be 2x. For the R2, right, this is R2 region, R mean is here, which is 1/2 x. R max is here, y max is here, and that's x plus y equal to 2, so that's 2 minus x. Okay. So that's the limits for the y variable. So 2 contact points. Okay, so then you try to figure out this x limit. Okay, x limits. Any questions so far? Okay. X limits meaning what do? You sweep this vertical line, right? Sweep this vertical line across this region R. So in this case, we're going to sweep this line across region R1, right? Okay, so you have a vertical line at here. Okay, you have a vertical line at here. Then you're trying to sweep this guy here. Right. Okay. So basically, you're gonna go find the edge right here. One is here, one is here, right? And the corresponding x value is the limits for the x. Okay. Okay. So then, apparently this is 0 here. So the question here is, what will be the x value at this location? Right. So I guess, how do you find that? You're gonna solve what? You're gonna solve this coordinates at here, right? And the coordinates, this is a point intersected by y equal to 2x and x plus y equal to 2. So let's call this is A point here. Okay? And we need this one, you call it B point. So for the A point, okay, for the point A, it's a solution of y equal to 2x and x plus y equal to 2. So that's an easy solve. And we should get, so plug the 2x to the second one here, so 3x. So x equal to 1, y, was that right? No. X is equal to 2 over 3, right? And y equal to 2 or 3 back over here, so 4 over 3. Okay? So which means my x mean for the first integral would be 2 over 3. Is that clear? Yeah. So take a look at this one here. Okay. Second one here, same thing. You're going to sweep this vertical line across the region R2. So basically from here to here, right? From here to here, okay? And the starting point for the x is this, which means the mean is 2 over 3. The end point is over here, so you need the x max, which is the x value for the B point, okay? So similarly for the B point, that's a solution between y equal to 1/2 x and x plus y equal to 2. So if you do this substitution here, 1/2 x over here is 3 over 2x. 3 over 2 equal to 2, so that's 4 over 3. Okay. Then y would be 2 over 3. So that's good. They just flipped, right? The A and the B points. So then x mean is this 4 over 3. Okay? Yeah. That's it. That's the integral limits for the two region. And if the question gives you f, x, y, then you will be able to carry out this integral. Okay? Yeah. So one of the quiz, maybe not next week, I don't remember which week, but anyways, the second quiz will be on double integrals. Okay? Yeah. Okay, so any questions? Okay. So when you give in the region R, okay, when you sketch, this is basically the reason why you need to sketch the region R. You look at the region R, then you will have better idea whether you need to separate into two, or you can just do it in one region. Okay? Yeah. So I want you to try the other way. What if you decided to integrate dx dy this order instead of dy dx? Okay? And then how would you deal with this region? So you can think of you can take a look at this one here, just initial thoughts here. Here's a region here, right? Here's a region. I guess you still cannot integrate this through this whole thing by one step. You still need to separate, right? So the way to separate it will be separating at here now. Okay? Yeah, so this is going to be your R1, this is going to be R2. So try to put down the limits for the two regions like this. Okay? Yeah. Now in certain situations, okay, sometimes you have a choice. Basically, in this particular case, doesn't matter which order you take, you're going to have to separate this into two regions. However, there are situations, if you pick this order, you're going to have to separate into two regions. But if you pick the other order, you don't need to. Okay, there are situations. For example, if you have a shape like this, okay. So if I do dy dx, I have to separate, right? But if I do dx dy, do I need to separate? No, right? Yeah. Okay, so sometimes that's the trick. You know, if you want to save yourself a couple of computation steps, right? Yeah, the order does matter actually. Okay. Any questions regarding double integral? Okay. Yeah, I think double integral is pretty straightforward. Okay. We have two different coordinate systems. One is Cartesian, one is polar. And all you need to remember is you use polar, okay, when the region R, okay, involves circular kind of area. Okay. And you use the Cartesian. Cartesian is sort of jack of tricks. You can apply the Cartesian to any different various of regions R. All right, so let's look at the applications of double integral. You know, basically it's sometimes called application for calculus, right? You know, what do you use? You usually learn single integral. You use that for some applications here. So we'll show some applications here. First, number one is area. This is very straightforward. So you can use double integral to calculate the area of a certain region. So that's pretty much explains itself. Here's the region R. Here's delta A. Then the area basically equal to you set your f function equal to 1. Okay, so that'll basically give you the area of this region R. Right? Yeah, that's very straightforward. And I think I'm going to skip the example here. This is just too simple. Okay? Yeah. So I'm going to talk the next one there. So I do have one simple example in the lecture notes. Okay, so second one here is to calculate the mass, okay, of a thin plate. Okay, mass of thin plate. The keywords here is thin plate. Okay, so thin plate basically means you can neglect the thickness of the plate. Okay, so that's what it means here. So basically you're neglecting thickness. So essentially, you're just calculating the mass of a certain area. Okay? Yeah. So in this particular case, you calculate mass. You calculate mass. You need a density function, right? Delta. So let's define this as a density function. Now, density function doesn't mean it's a constant. It can be a function, variable density. So in other words, the delta here can be a function of x and a y, right? It can be function x, y. And to calculate the density, so what you do is you can select a very small area, then the delta m equal to this delta, okay, multiplied by delta a. So that's the small mass for the small area. Then you add all this up, you get a total mass, right? And when you add them up, you end up with a double integral. All right, so yeah, so this is nothing different actually from a regular definition of double integral, and all the difference here is you're essentially giving that fxy function a meaning, which is the density. So that's the only difference here, right? Okay, yeah, that's mass. Okay, the third one here is average value. So average value of fxy over region of R. Okay, so average value of fxy over region R. Okay, so this average value is a very important concept when you learn statistics. Okay, so let's start with the most simplest case here. If I give you a whole bunch of numbers, A1, A2, up to AN, okay, whole bunch of numbers. So what's the average? The average would be A bar equal to, oops, right? That's the average, right? That's the average. Okay, yeah. Okay, so then the similar question here is this. How about if I think of this way here now? Yeah, how about this? This is the first case, and let's see the second case. Okay. Now let's say I have a function now. Okay, I have a function fx here. It goes from A to B. Okay, it goes from A to B. Now I'm interested in this. I'm interested in the average value of this function f when you're going from A to B for the x value. Okay, right? So now you look at this situation here. This is not a discrete. This is continuous, right? This is continuous case. Yeah. So if it's a discrete, let's say I have a bar here, bar there, right? So what do? You add all the value up and then you divide it by the numbers, right? Yeah. But now you have this as a continuous here. So what we'll do is we can still make use of this kind of a discrete sense using the limit concept here. Okay. So I'm talking about the average of this f here. Now, what is the value of f at a particular point? Xk is what? F of xk here, right? F of xk. So I'm talking about this value, the average. So essentially, I'm saying is I'm talking about this guy here. But what I'm going to do is I'm going to change this value of xk, right? And maybe I'll separate into n number of portions here. So then I'm going to add all of those value up, right? So you see, I have n number of basically straight lines here, right? Then I add all of them up, and then divide it by, let's say, total n here. Okay, so that's sort of approximation, right? That's sort of approximation of the average of this function f over A to B. Okay, yeah. But that's approximation. Doesn't mean it's not accurate. Okay, so this is basically an approximation. Now, what we're going to do is let's do this. So let's say this is y bar at here. Okay, this is y bar. Okay. So average of this function. Average of f at here, which is the y bar. Okay. Now what I'm going to do is I'm going to multiply. Okay, here I'm not going to change anything here. All I'm going to do is I'm going to multiply delta x at the bottom here. Okay. If I multiply the delta x at here, then what do I need to do? I also need to multiply a delta x over here, right? Okay. So this delta x will cancel this delta x. Nothing will change. So delta x basically it's a small value around this xk. Okay. Small length around this delta xk here. So how many delta x here? I have n number delta x. So technically what happens is when you multiply this n with delta x, what did you get? You get what? The length from A to B, right? Exactly. You get B minus A, right? You get B minus A here. So this n delta x equal to B minus A. Okay. So that, okay, like this. Now let's increase the number of n. Let's let n goes to infinite, right? Let n go to infinite. Now if you go n go to infinite, then this term here, this is a summation here, right? Summation. Then summation becomes what? An integral, right? So this y bar basically is b minus a integral a to b fx dx. Okay, yeah, dx. So this is basically the average f over the range of a to b. So then I come to the case number 3. And I'll draw the number 3 here as the case of this. Here's the region R, okay, and we have a function fxy. Maybe the function xy is something like this. Okay, so it's sitting on the top of this R here. Okay, sitting on top of this region R. So now my question here is, what is the average value of this f over this region R? Right, so that's the question here. What is the average value f over R? Okay, over R. Come again? The area of the region, that's right. Yes. Okay, so I think you get the idea now. Well, if we're going to use this similar thing here. So what happens here is, this is average f here, right? Now, I'm talking about average this f here. So this f appear to this region R. It's basically, it's like what? It's like a height, right? It's like a height here. So if you think of this as a 3D object here, so what we're doing here is we're trying to get the average height of this 3D object. So you have this 3D objects here. The bottom is flat, and the top is irregular. So what's the average height, right, of this 3D objects here? Okay, so this is sort of the idea of average height. Okay, average height. If I use the same idea here, average height is h bar. Okay, let's call it h bar here, which is basically the f bar we're looking for, right? Yeah. Then I'm going to take maybe n number of heights, and each one of them are taking at xk, yk. So there are n number of heights set here, okay, n number of heights. Then we're not going to change this expression. All I'm going to do is I'm going to just multiply this delta A over here. Then I will have to multiply another delta A over here, okay, to make sure nothing changes, right? Yeah. So this is average height, and this is just manipulation here by multiplying a delta A. And the n multiplied by delta A. Delta A is a small area over here, right, underneath this, in this region R. So n multiplied by delta A basically give you what? The area of this region R, right? The area of the region R. And as n goes to infinite, okay, as it's going to go to infinite, this whole chunk out here becomes 1 over area of R, then multiplied by a double integral. Okay, over double integral. So this is basically the physical meaning of what this expression means. Okay. So when you use a double integral, okay, which is function f, integrating function f over the region R's area, what you get is the physical meaning. What you get is the average of the function f. Okay, yeah. Now, when you learn a statistics course, you probably will see this kind of formula again. Okay, double integrals. Okay, so any questions? Okay, so I can call this, instead of calling this h here, this is also f here. Okay, same thing. Okay, this is also the f bar here. I'm just using the height as a physical quantity, average height as a physical quantity. Okay, so this is average height here, right? This is average height. Now, what about the other physical meaning? How about, right, if f here doesn't represent the height, if f here represents the temperature, Okay, so F here represents the temperature. So you have this region R here, and F represents the temperature at a different location on the plate. Then if you carry out the same calculation at here, what would you get? You get what? Instead of calling average height, you would call it average temperature. Okay, average temperature. Now, same thing, if F here, right, represents maybe a distance. It's a distance of a certain point to if fx is represented the distance, okay, it's the distance to a fixed point, okay, to fixed point P, okay, to fixed point P. So over this region R here, you know, this is a point P, that's the distance, right? That's the distance here, okay? Then when you calculate this using this double integral here, this formula, so what you're going to get here, you're going to get this basically average distance, okay, average distance here, okay, to P. Okay, so this 1 over area RF dA, right, basically is the average distance to that point P. Okay, yeah. Okay, so this is the concept average. Any questions? All good? Yeah, that's the third application. Okay. So next time when you see integrals and this kind of expression, okay, try to relate that to the physical meaning. Okay. The fourth one is called weighted average. Weighted average of F. Okay, weighted average F. So what is the weighted average concept? First of all, let's talk about the weighted average, right? Weighted average. When you calculate an average, right? Suppose that I have a data set, okay, x1, x2, up to xn. Okay, I have data set x1 to xn. Maybe the probability of, well, this is probability. The probability of for each one of them to happen is the same thing. Okay, maybe the same thing, but maybe not, right? Maybe some of them happens more frequently than the other ones, right? So then, when you try to calculate the average of this quantity here, then at x bar, what you do is you multiply a weight. Okay, you multiply weight with each quantity. Okay, with each data. Then you divide it by the total weight. Okay, divided by total weight. That's so-called weighted average. Okay, that's what they call it, weighted average. So usually in probability concept, the value of W1 multiply adding up to Wn altogether equal to 1. Okay, equal to 1. So 100%. Okay, so now if I apply this idea to the weighted average of function f, okay, so what do we do? So basically, I'm going to use this density concept here, okay, using the density concept. Okay. So you have a region R here, okay. There is a different density, okay, at a different location, okay, on the region R. So in other words, if I take a small area delta A here, okay, small area delta A, and there's associated density delta, okay. So we're going to think of this delta function, okay, as the weighting factor. So you have at each delta A, you have a weighting factor delta, which is the density, right? Yeah, which is density. Now, if I wanted to calculate this, the average of this one here, so what we do is this f will simply becomes, okay, this function xk yk, let's say at this location, okay, it's xk yk, multiplied by delta, okay, xk yk delta A. and divided by this delta xk yk delta a. Okay. So basically, the weighting factor, instead of the weighting factor, is just this one. Weighting factor is this. Okay. This is the weighting factor, sigma. K equal to 1 to n, k equal to 1 to n. So this is the weighting factor. Okay, wk. Okay. So
what is APSC248?
this is a function, the function we're trying to calculate the weighted average of this function f here.
So how does density times area times function reach what? Volume?
Hang on a second here. What am I doing here? Yeah, that's right. Yeah. No. Okay, so you have this function f here, right? And the half function f. This function is different from the delta here, okay? Function from delta here. So this function just a second here. Yeah, okay, so this function here, right? This function here is going to be weighted by certain things. You know what I'm saying, right? So for example, see here, this is x1, x2, xn here, right? Each one of them weighted by w1, w2, wn. That makes sense, right? So now I'm doing the same thing here. If I consider x1 as this f, x, k, y, k, is that okay, right? Consider x2 as f, x2, y2. And w1 to wn as the weighting, basically, it's a weighting matrix taking out of this region R here, because I'm trying to relate that to the region R, okay? Yeah. Then, if I multiply this with delta A, that's a mass. So at a different location, I have a different mass. It's like I have a different weighting. That weighting factor multiplied by this function, f value, at that location, that's like this term, this term, this term here, okay? And the bottom here is basically adding all the weighting up, right? That basically gives us so-called average f. Now I'm using this delta as a density concept, right? But if you think of it purely as a mathematical concept here, this doesn't have to be a density. Okay, it can be just a simply math expression here. You think of this whole thing as a weighting factor. And as n goes to infinite, this whole chunk here, you have basically, the top here is a double integral. Okay. The bottom here, when you integrate this portion here, what do you get? If I consider this delta as a density, density by delta A is a small mass at one location. When you add all them up, you get what? That's right, you get total mass, right? Yeah. So this is basically the weighted average, okay? Weighted average of this function f. Okay, function. Yes, it will be double integral. However, you know that double integral give you is the mass. Yeah. Yes. Yeah. Yes. They all integrate over the same region R. Good point. Yeah. Okay. Yeah.
The delta, is that just your density function?
Yes. In this case, you consider it as a density. That's good enough. Yeah. Yeah. But if you just if you look at this one as a pure mathematical expression here, it doesn't have to be a density. Yeah. Okay. Very good. So that's number 1, 2, 3, 4, 5. Sorry, this is 4, right? So all we're doing actually is for the purpose of number 5 and number 6 and maybe 7. All right? Yeah. Okay. So before we move on in here, okay, let's look at this one here. What happened when delta equal to 1? If delta equal to 1 here, what does this f bar give us? Exactly, right? It gives us this number 3 at here, right? Give us number 3. So if this gave this delta 1 here, it gives us this number 3, average of f here. Instead of weighted average, it gives us back this traditional average. Okay? Yeah. Okay, so number 5 is the center of mass. Center of mass. Yeah, if you're going to mechanical civil, okay, chances are the formulas listing in here for the double integral and also triple integral, I would recommend you remember them by heart. Okay. Okay, center mass. I think this is not a new concept, and basically we're talking about center mass for certain region right here. Okay, it's somewhere over here. Let's see. Okay, somewhere over here. Okay. So I'm going to call it x bar, y bar. Okay, x bar, y bar. Yeah. So what is the concept of center of the mass then? Right? Why would you call that as the center of the mass? What would be the physical meaning of why? Why is it called a center of mass? Because the center? Yeah, why? Right? Come again?
All the weights at that point.
All the weights in the center of the point. Okay, that's good, right? Yeah, that's one way of doing it.
So
yeah.
You can evaluate it as a particle?
As a particle, yeah. And the other, yeah, that's good. But let's say if I want you to think of in terms of the moment concept. Okay, the moment concept here. So if I have a particle here, what's the moment about certain axis? It's the mass of this multiplied by what? The distance here, right? Multiplied by distance. Okay? But now you have a whole mass here. And I want, as Newton said, I want to think of it as one particle. So basically I say, what is the moment of this object about this axis, for example? Right? So, you know, if you know, okay, look, I think I know this is a total mass here, m, right? But I just don't know what should I multiply the m with? You know what I'm saying? Right? You know, m multiplied by distance give me the moment, right? Give me the moment. If I know the distance d, so let's say I'm talking about the moment of this vertical axis here. So m by d give me the moment. So that d here is actually the what? The center of mass for the x coordinates, right? The x coordinate is the center of mass. Okay? Yeah. So basically, what you can do is to find the center of mass. Let's say I'm trying to find the x coordinate of the center of mass. So x coordinate of center of mass, this distance here, right? This distance here. Okay, and here's m here. This m here. Well, I guess I should call it mg here, right? Okay. So I'm really looking at. Let's just use m here. Mx bar. Okay. I'm trying to look at the value of mx bar here. Okay. So mx bar is the value, it's like a moment created, okay, about this y-axis, right? Okay, a torque. Okay. So what does that equal to? That equal to, if you separate, right? If you separate this region R into many small areas, as many as possible, that equal to the total moment created by each one of the small area. Does that make sense? Right? Each one a small area. What is the moment created by one small area? It's the mass of that small area. Mass meaning it's the delta A multiplied by delta, right? For the density. Okay, by density here. So I will use a delta. I'll write it differently. Okay, I'll use delta xk yk delta A like this. Okay, that's the mass for one small area. The mass of this one small area multiplied by which quantity give me the moment? No, multiplied by what? xk, right? xk is the distance right here. From here to there, that's the quantity, this xk here, right? So this multiplied this give me the moment created by this one small mass. How many do we have? We have, that's n number of them. And I'm going to let n goes to infinite. Then this whole chunk over here becomes, what does that become? Become a double integral, right? Become double integral here. So x just x. Okay, become double integral. What we're looking for is x bar. So that means what? That means my x bar just simply equal to 1 over the mass, then r x dA and here. Okay. So this is the mass of the plate R. How do we find the mass? We found the mass from where? From, have we found the mass yet? Yeah, from here, right? From here. Okay. So that's X bar. Then what's the Y bar? The average is going to be Y here. D8, right? D8. All right? Yeah. So this is basically the center of the mass. Okay. It's a balanced point. Now, as a matter of fact, if I look at these two equations here, and if I compare the two equations with two expressions with this average with this one here, this is the formula for what? The weighted average of function f, right? This is the weighted average of function f. All I'm going to do is I'm going to change this f to x. If I change this f to x, what do I get? I get this guy here, right? I get this guy. If I change the f to y, I basically get this guy here. Okay? Yeah. So basically, this is a weighted average concept, these two. Okay? Yeah. Does that make sense? Of course, right? You're looking for the x bar, the average of the x. So you're basically weighting the axis from where from, within this region R there, right? Yeah.
Why do we need to classify what kind of average are?
Why do we what?
Why do we need to classify or distinguish like what sort of average they are, whether they're weighted or normal average?
Oh, you mean how would you tell whether this is a weighted function or not?
Why would we tell that? Like,
why do I need to point it out that? I just trying to establish a connection in here. This is basically weighted average of x, right? And this is weighted average of y. Okay. Yeah. Okay. So number 6. Okay. Number 6 is the moment of inertia. Okay, moment inertia of the area. Okay. Now make sure you understand this one here. Moment inertia is a very general concept here. Right now we're talking about moment inertia of the area. Why is it area? Because it's a plate, right? Thin plate, which is represented by the region R here. Okay. So this is not the moment inertia of a 3D object yet. Okay. So in mechanical terms, sometimes this is called second moment of area. Okay. Second moment of area. Okay. Now you probably say, is there the first moment? Yes, there is. Okay, that's different. That first moment is polar. Okay, so remember the difference here. Okay, this is talking about the second moment, the moment inertia of the area, not the moment inertia of 3D objects. Okay, so what is the moment inertia concept here? So let's start from the simplest concept here. Okay. First of all, what is the concept of mass? When you're talking about the motion of a certain an object, right? And you had to think of the mass. So what does the mass have to do with the motion? The mass will do what? Always a call. Come again? Yeah, exactly. The mass will generally oppose the motion here, right? The heavier it is. So motion basically means you're trying to push it. The heavier it is, the harder it is, right? So the mass essentially means how hard, right? It's how hard it is, to impart a translational motion. Okay, so that's the mass. Okay. So you have a point mass, you're trying to push that at a certain speed. The heavier it is, you need to the more difficult it is. Now, then the next question here is, what about this moment of inertia? Okay, this concept here. So moment inertia is a concept. It's a concept always about certain axis. Okay, so it's a concept always about certain axis. So I think you probably can translate this mass concept to this concept now. So moment inertia would be what? How hard it is to impart rotational motion. Okay. Okay. So that's the concept moment inertia. So you have a cross-section area here, okay, and that's the plate, and you're trying to rotate the plate around certain axis. Then it's thin plate. Then the larger the moment inertia it is, then the harder it is to initiate this rotational motion. All right? Yeah. Now let's talk about this. First of all, let's derive this. I'll call it MOI. Okay, I'll call it MOI, moment inertia. Let's look at the moment inertia with respect to origin. Moment inertia with respect to origin. So what does that mean? So that means here is a region R at here. Okay, here's region R, right? So now I'm going to do is I'm trying to initiate a rotation of this R with respect to an axis going through this origin here. So which means which axis are we looking at? The what? The z-axis, right? The z-axis here, okay? Yeah. So with respect to origin, or basically z-axis, okay? Z-axis. Okay. So we start from kinetic energy, okay? Well, I'm going to try to derive this one here, okay? Trying to derive. First, kinetic energy. Okay, kinetic energy of point mass. Okay, so let's call that small m in here. Okay, so kinetic energy of point mass. Okay, moving at velocity v. Okay, just use no vector. Let's just use a v at here. Okay, so you have a point mass moving at a velocity v. So what's the kinetic energy? 1/2, right, mv squared. Okay, yeah. So now suppose that the v is doing this. Okay, suppose that this is m right here. Okay, this m here, this is v here. So actually, you know what? The m here, okay, is actually doing certain kind of rotational motion. Okay, rotational motion. Rotating about where? Rotating about this. Let's say maybe this axis here. Okay, yeah. At that particular instant. Okay, particular instant. So this is basically the trajectory of that m here. Alright, so I'm going to make use of simplification here. So let's say after certain angle, delta theta, okay, your m is here, okay, yeah. And it's moving about this one with the v at here. And this is v. And this is r, okay, this is r. Okay. Then, how do I find the relationship between the v and r and the theta? So what do? We do this one here, right? We do this. So the v, you know, basically v equal to ds over dt, okay, over ds over dt. And how much ds is basically the displacement. In this particular case, when you travel from here to here, that's the ds, right? That's the ds. So this ds can be calculated or can be expressed using the r and the theta. So you consider this as r, so that ds will be simply r d theta and dt. Okay. And what is d theta over dt? It's the derivative of the angle, which basically is what? Omega. There we go. So that's the v in terms of r and omega, right? Okay. Then my kinetic energy, okay, for this point mass, so the 1/2 mv squared will be simply, I'll replace the v with r omega. So 1/2 m r squared omega squared, right? Then, in this particular case here, right, I'm gonna combine these two together. Okay, combine these two together. So I get 1/2, okay, I omega squared. Okay, I call it I naught maybe. Okay, and I naught equal to m r squared. Does that make sense? Yeah. All good? Okay, so what's this guy here? This is basically what we call the moment inertia of this point mass with respect to origin. Okay, so this I naught here, okay, is the moment of inertia, okay, of this point mass, okay, with respect to origin, okay, or with respect to an axis, okay, passing through that origin vertically. Okay, yeah. That makes sense? Yeah. So here is a point mass with respect to this origin. Then when I go back over here, right? When I go back over here, how many point mass do I have here? They're infinite, right? They're infinite. So I have here, 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 right? Right here, here, here. Yeah. So then if I wanted to calculate the moment inertia of this R with respect to the origin here, what do? I basically add all this moment inertia of each one of the point mass, right? Add them up. When you add them up, that basically is the concept of what? When you add them up, what? So okay. So here it is, right? So delta mk rk squared. So that's one moment inertia of one particular delta m, right? For delta m. So what do we need, right? This delta m here, if I know the density, and that's basically delta xk yk multiplied by delta a multiplied by rk squared, right? That's this guy here, right? Yeah. And what do? We add them up, right? We add them up. How many we add? We add up to n. We let n goes to infinite. So then this summation becomes double integral, right? Double integral. So as n goes to infinite, you get a double integral here. And that double integral, this is the moment, this is basically the I here, right? This is the I here. The I equal to summation of each one of them. And as n go to infinite, you got a double integral. So looking at this double integral here, what are we integrating? We're integrating what? There's rk squared here, right? Instead of rk, you can just write r squared. And multiply by delta, which is the density here. And then dA at here, over r. Okay? Over r. Okay. That's it. That's the moment inertia. That's the moment inertia. So this guy here is the moment inertia of that plate R, or the region R, with respect to the origin. Okay, respect to origin. Yeah, sorry.
What's R, like R is going to be changing?
Yes, R will be changing. So basically, if I have region R over here, right? If you have a point here, this is R here. If you're here, that's different R. Here, that's different R. Yeah. So that's actually, you're going to have to basically integrate. So the R here is what? So R here is actually, if I pick a point inside here, and this point is x, y, what is my R then? Right? That's my R. Okay? Okay? Yeah. So then this actually brings to the question here is, you know, how am I going to calculate this one here? So you can either calculate using Cartesian coordinates. So these are Cartesian coordinates here, right? Or if the region R is a certain kind of circular motion, so then you're going to you can convert everything into the polar coordinates, right? Yeah. So if I convert in the polar, that dA will be r dr d theta, okay? And this will be r. Okay, so if I write it a different formula, this will be r squared, and this one here will be delta r cos r sine. Okay, so that's basically the formula in terms of these polar coordinates. Okay. So if you wanted to count, then if you're going to calculate, basically if this is rotating, if the people ask you is what is the kinetic energy of this objects here, so you can calculate just basically 1/2, right? I omega squared. Okay. Yeah, that's another formula. So rotational kinetic energy. All right. Now remember, this is basically the I with respect to the origin here, right? Now what about if the question is the question here is, how about let's see, what about this the moment inertia about, let's say, maybe x-axis. Okay, so you have a region R over here. Okay, and you're looking at the moment inertia about the x-axis. This is x-axis. Basically, you're trying to initiate a rotation of this R about this x-axis, and you wanted to know how hard it is, and that will be represented by the moment inertia of that I there, right? Yeah. So this is called Ix. Okay, Ix here. So in this particular case, so this I here, this is moment of inertia about, okay, origin. Okay, origin here. So what can I do to change this formula to get this Ix here? So yeah, R becomes what? Y. That's right. So because any point to that axis, the distance is y, right? So basically this becomes y squared delta xy dA. Okay, yeah. And if we're talking about iy, then x squared delta xy dA. Okay? Yeah. That's it. That's how many applications here? 1, 2, 3, 6, right? Yeah, 6. So that's all we need, okay? Yeah, for this one here. Moment inertia, mass, center of mass. Okay, yeah. Okay, so we still got time. Let's now look at a question here, okay? Let's look at the question. We'll mainly look at examples of the last application, basically calculate the moment inertia. Okay? Okay, so first example, I'll give you a disk. Here's a disk with the radius of A here. Okay, and I want to find the moment inertia of this disk with respect to origin. Okay, so I want to find this quantity here. All right, yeah. So that basically means I'm going to use which formula? I'm going to use this formula here, right? This formula. Okay, yeah. Okay, so my I with respect to origin is going to be R squared here, delta xy dA. So assuming delta equal to 0 to equal to 1, where the density is even, evenly distributed everywhere, it's 1. Okay. So then let's see what this quantity is. Because the region R is a circular area, so I'm going to use what? Polar coordinates. So then if I use the polar coordinates, the dA becomes R dr d theta. So we need to find out the limits for this R and the limit for the theta. And that's basically a regular double integral problem. So what do? You draw a reading lines out of the origin. You find the first contact between this reading line and the region, and that'll be the limits R mean for this R. From the second contact, that'll be R max. So technically speaking, this is what? A0 to A. Then you sweep this reading line across this whole region R. Find the mean value for the theta and the max value for theta that bounds this region R. So in this case, 0 to 2 pi. It's very simple. So this is easily can be calculated, which is pi a to the power of 4 over 2. Okay. Yeah, you have a table handbook. Generally have a table for commonly seen geometries. You know, the moment inertia, second moment inertia, for different regions. But this is basically how did they calculate it? Here's how you calculate. Okay, yeah. Okay, one more example. Same disk. Okay. Radius is A, but this time it is okay. What we want is we want to calculate the moment inertia about an axis going through any point on the edge of this axis, okay, and a vertical perpendicular to the disk. So we want to know what is, okay, let's say it's rotating about here, and there's it's an axis passing through any point on the edge, and what will be the I, okay, about, okay, an axis, okay, through a point on the disk edge, okay, yeah. And the perpendicular, okay, yeah. So that's this second example here. Okay, so in this kind of thing here, what we need to do is we need to set up ourselves a certain coordinate system first and place this whole thing in the coordinate system here, okay? There are different ways of doing here. So what we're going to do is we can try this one here. Suppose that we're going to place our disk, okay, into this coordinate system. Okay, so essentially, here's XY coordinates, and we're looking at this basically, okay, that's axis going through this origin over here, right? This axis going origin here. Yeah, is that right? Okay, so that's what we do it here. Okay, so if I do this one here, okay, so then we're calculating, okay, the moment inertia. First of all, right? What is the formula of this one here now? So I need to use what? Oh, yes, assuming the delta is still equal to 1 here. Okay, assuming the delta is still equal to 1. So what's the formula? R squared. So if you pick any point, okay, on the disk, then you calculate distance from that point here. That's R, right? That's R. And it's R squared, delta is 1, so dA. Okay? dA. So this is the current I here now, right? This is current I. Okay. Same formula basically. Actually, it's the formula-wise, right? Formula-wise, the same thing, right? Same thing. Does that make sense? Yeah. Moment inertia about this axis going through here, vertical. So you need a distance from that point to this axis, which is R squared here. Okay, so the trick here is this. How do I find the limits now? So it's still circular. I think I'm still going to use polar moments, polar coordinates. So what do? We draw a reading line, right? We draw a reading line across this whole region R. First contact, give me the R mean. Second contact, give me the R max. So what's the value of R max? 2A? Is that 2A? No. If I draw it here, it's 2A, right? If I draw it here, it's less than 2A. So it's a changing one, right? So the R max is not a constant. So what do? What's the value here? This is what? 2A here, right? It's 2A. If I connect this point with this point here, what kind of angle, what kind of triangle am I looking at here? It's a right triangle. And what's this value here? Theta. So now, can you find a relationship now between your R max and 2A, which is what? 2A cosine theta. So your R max, here your R max, equal to 2a cosine theta. Alright? Yeah. As a matter of fact, this 2a cosine theta is a circular, it's an equation, polar equation in polar coordinates for this circle. Okay, and here. And and that's R, right? And theta is you rotate this reading line across this whole region R. Find the mean and the max for the theta that bounds this region R. So what will be the theta's range? 0 to pi? No. Where does 0 start?
Negative pi over 2.
Negative pi over 2 to pi over 2. That's right. So here's one bound here. The other bound is up, right? For this one here, it's negative pi over 2. For this bound here, it's pi over 2. Okay? Can I use a different value over here? Instead of using negative pi over 2 to pi over 2, what else could you use? So, negative pi over 2 is you count it from here, right? So how about if I count it here up to here, what's this value? No. Yeah, 3 pi over 2, right? And I keep going up to here. So this bounds here, instead of a pi over 2, could also be. So you go all the way back here. How much angle did you rotate? 5 pi over 2. So if you use these limits here instead of this, you should have the same results here. Okay? Yeah. As long as you're consistent, basically, you're consistent of using the angles here, right? Yeah. Okay, so then this integral here, we're not going to calculate here. I'll just show you what it is. Okay. Let's carry out this integral here. Just see what's that they're going to give us here. Okay. So I'm going to use this one here. So the middle one here is, this is R cubed, and the integral of that is 1/4. What am I saying here? Yeah. So here is 1/4 R to the power of 4, 0 to 2a cosine theta, then d theta. Okay, d theta, right? Yeah. Yeah, practice this integral. It's actually a pretty challenging integral here. So what do I have for this one here? I have, so plugging this 2a cosine theta into this r to the power of 4 right here. 2 to the power of 4 is 16. 16 divided by 4 is 4. So you end up with a 4a to the power of 4 cosine theta to the power of 4 d theta. Okay, d theta. Okay. So now the question here is, we need to integrate this guy. Okay, we need to integrate this guy. Yeah. I'll give you a trick here. Okay. If this is a sine theta 4, guess what's going to be the result? Sine is a odd function, and the limits here is even. It's symmetric. So when this is odd function here, the integral of odd function. Sorry, actually, the sine not good. So sine theta to the power 4 becomes an even function too. Okay, forget about that. If this is just a sine here, if it's just a sine in here, the integral will be 0. Okay, yeah. And this is an even function, so the integral can be, instead of this, can be 2 integral 0 to pi over 2. Okay, but that doesn't really help actually. So for this particular case, you can either use a formula, so you can try to look at the table, or you can use what? Integral by parts. Okay, by parts. So take a look at lecture notes as to how this is carried out as an exercise. Right? Yeah. You could, but I think it's more complicated. Actually, you know what? It would be, because why? If you split it up, right? If you do this, see, you end up with a term cosine 2 theta this. So
for this question, can you also do it for the cube of pi? And just switch this to
yes.
because there's still a pi difference.
Yes.
That would work.
You should end up the same result.
Right, okay.
Yep.
Still does not make sense to me. If I want to find x, the center of gravity, I'm going to do the moment across x-axis, right?
About the y-axis. So we're talking about, let's say, you're looking for x bar, right?
So wouldn't that be the moment around y if I want to do across the y-axis? That would give me the y moment.
No.
That would give me the y.
No. Okay. So to initiate the question here, hang on a second here. Yeah, that's right. So we're trying to look for x bar, right? Yeah. So we're saying, okay, I'm trying to calculate what is the moment inertia? What is the moment? What is the moment about this vertical line?
That's going to give me x bar.
Yeah.
Moment across this vertical line.
Yes.
That'll give me x bar.
Yes.
But I would be integrating from like here to there. Wouldn't I get
No. Forget about integration first, right?
Okay.
Yeah. Just think about it. Does that make sense? I mean, the moment about this axis is what? Let's say, what's the moment at this point about this axis? It's the mass of that point multiplied by this distance, which is the x coordinates of that point.
multiplied by this distance.
Say you pick a point, right? And suppose there is a small mass around that point.
Yeah.
Or pick a small area. Very small.
Okay.
At a certain location.
Okay, if I pick a very, very small area, this is my x, this is my y.
No, not this x. This is delta x, that's delta y.
The delta x,
Yeah.
delta y.
Yeah, then x basically means it's the, let's say, here is x, and that's y. Right?
Then I want to find x. X would be...
You don't want to find x. You want to find the moment created by this small mass about this axis.
Okay. And that means I would have to...
Or the torque, doesn't matter.
That means I would have to be doing dy times x.
No, not dy, right? Moment is, you need to calculate the moment is the force multiplied by the distance.
Yeah. And then the force...
The force here I'm talking about, forget about gravity, just m here, right?
Yeah.
We're thinking about m, the force. It's a small m at here, multiplied by the distance, which is the distance from here to here to x.
That would give me for the y though.
For what y?
That would give me for the moment created by the y.
No, created by this axis, about this axis.
Okay, but because what I'm still confused is that if I want to find the x torque,
Yeah.
I mean, if I want to find the moment across with the x torque,
Yeah.
right?
Yeah.
Which means I'm trying to find the moment that if I was to rotate the center of gravity.
No. See, when you're rotating about the x-axis, what is the distance? From there to there is always a y,
Yeah.
right? You just think about a point mass in here first. If I just have a point mass here,
Okay.
you want to rotate about the x-axis. What is the distance from here to the x?
Y.
Y. It's not x.
So then, therefore, wouldn't this be y?
No, it's x.
Okay. It's because it's confusing to me because I'm thinking I'm rotating this mass.
Yeah.
And I'm trying to find the center of gravity of the mass, right?
Yeah.
And I find the moment times the center of gravity in x, right?
Not a moment. That's m.
This is my moment.
Okay. Yeah.
And this is to find the x to find the x.
X bar.
To find the x bar.
This is the moment about which one?
This is to find the x bar.
Okay, no. Mx a bar, is this the moment about which axis?
Wouldn't it have to be across this axis?
No. Why? About the y axis. From there to there is x.
Okay.
Right? Force by the distance gives you the moment, right? And this is the distance from their point to here, which is the x-axis.
Okay. 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 I have class, but I might come.
Yeah, sure. Yeah.
I have a
Yeah.
question. How did you do?
Huh? How do I what?
How did you convert?
How did I get that value?
Go up.
Yeah.
These two values. Like how do you
Oh.
convert this to?
Okay, so it doesn't matter, right? See, this is here are the bonds, right? Here are the two bonds, right?
Yeah.
So you look at the bottom bonds here. If I started from here, going all the way to here,
Yeah.
how much angle?
370. That's 3/2.
That's 3 pi over 2.
Yeah.
Then I keep going up to this next bond, which is 5 pi over 2. That's why it's max.
But you start from here.
Yeah, starting here, right?
Yeah.
Going all the way first is the lower bound,
Yeah, lower bound. Oh.
then to upper bound.
Okay.
Yeah? Yeah.